Okay, yeah. So next up we have Nada talking about Holey.
Yeah, so this is staged execution from Python to SMT, and the goal here is really to do it for synthesis. So let me show you an example of what that means. So we might have a predicate, a SAT predicate. Here it takes a string, so S, and we want to find an S such that the SAT predicate holds. And here we're saying that we count the number of O's and we get 1,000, and we count the number of OOs and we get 0. And so as a human, you can probably find a constraint for such a string. When we ask an SM, so going through the Holey pipeline, when we, oh. The screen changed a bit, but I'm not sure what's going on. I'll put it back. Is it?
Try replugging it again, maybe.
Well, okay. There's something on. I don't know what changed. Something changed on the resolution, but I think it just shows the 3 instead of 1,000, you might get this solution, which works. And then if you ask an LLM to extrapolate from 3 to 1,000, it might come up with an expression like this, among others, and this one actually works for this example, for the original example of the original size. So we're going to play with these ideas today and look at, in particular, try to find solutions to such puzzles automatically. And the goal is really to play with SMT as a backend and thinking of it, how well can it do synthesis in that context, synthesis of values. So the way it works in the more general case is we're given a predicate in Python, and then we try to find a witness to pass to this predicate so that it returns true. And then whatever we do with the solver, this is where Holey lives. Whatever we do, we recheck at the Python level to make sure we haven't made any soundness issues, soundness mistakes, and things like that. And so the general approach is quite simple, especially if you're familiar with multi-stage programming. The idea is that we overload execution by having symbolic variables. So when this Python program executes, the x variable is symbolic, and then that means that this expression x greater than 5 is lifted symbolically. And then as a side effect of running the Python program, we get this SMT constraint generation, and we then are able to use an SMT solver to solve for this, return a solution, recheck at the Python level. So that's how it works. And in terms of the underlying approach, so we really have, for these symbolic variables or these symbolic expressions, we have a dual representation, something concrete that allows us to propagate constants and have as much information as possible, and something abstract that is about the SMT, the underlying SMT expression that we want to generate for this symbolic value, so symbolic int, symbolic string, or whatever type we want. And in our system, mutations and other features only exist at staging time, so we don't need to have the whole Python semantics completely understood. We can just generate code based on the execution of the Python program. And some virtualization happens through AST rewritings. At first, I wanted to do a lot of the things using Python metaprogramming and overloading, but really, in some sense, to lift built-ins, you have to do a little bit of AST rewriting and things like this. For if, this was just a way to do some optimizations with the other things that I'm going to mention later, which include conditional exploration. So here we can kind of simplify a mutation inside a condition with a rewrite to the if-then-else expression of an SMT solver and things like this. So we can, in an ad hoc fashion, add more or less optimizations just based on what we want to achieve, and sort of like doing it incrementally to get as many of the benchmark as working as possible. So in terms of the conditionals becoming path exploration, if we have some SAT expression like this in Python, what we have here is when we have this expression, eventually when we want to execute the if statement, Python will call this __bool __ function that is possible to overload at the user level. And so we play this trick of doing a path exploration through the overloading, and I'll get back to this. And just for the intuition here, we basically consider all branches and then guard the branch with the conditions, and then emit implications for these things. So in terms of the overloading of bool, so we kind of pick a path, record the constraints. We have the choice which path to pick first, and we might just pick randomly, or we might just pick deterministically, like maybe a best path or something. And then the driver loop reruns with opposite choices until all paths are explored. So it's not that cheap in some sense. We're doing extra executions, but it's a poor man's way to do like staging of branches, and it has been done in other contexts. So my inspiration over this was Phil Zucker's blog post on picking, where he does something like this in Python, but he picks a branch randomly instead of exhaustively. And there's also the built-in staging library in C++ that does something similar for path explorer. So even if your language is not extremely powerful with virtualization, you can still play tricks like this. And so another thing we looked at is encoding lists. So we can either use recursive lists as a data type at the SMT level and basically have kind of lifting what this Python code does using SMT functions that are defined in the target. Or we can also do a thing where here we actually know that the length of the list is 5, so we can explode it into variables at the SMT level, and this is quite more tractable for the SMT solvers to deal with these exploded encodings on bounded lists. So when I first started this project, I tried to use solver bindings in Python. I thought it might make things easier and would allow me to do more different things, but it turns out it was quite hard to get it not to segfault, and using an SMT-lib target turned out to be more portable, like having more targets, and also led to collaboration with Kartik from the CVC5 team, kind of trying to see how he could run my benchmark in a faster way. And so the research benefit here is that by using the SMT-lib target, we are able to do these, to kind of research these solver-facing encodings as artifacts as well. And there is also a benefit that different solvers do different things. So for example, in our data set, we see that 150 or so are uniquely solved by Z3, 40 uniquely by CVC5, and the majority of them by both. And one thing that happens here is that we do have, because mutation is not understood in the back end, and we also have this problem that we don't actually do any sharing. We could, but turns out we don't really need to do too much sharing because the SMT solvers can handle the explosion that happens here for the problems that we looked at. But basically, in a problem like this, you end up with trees that gets exponentially bigger with the range here n because of that setup. And in terms of results, so this was when the talk was proposed, these were our results. Since then, just by iterating, like just trying to do more things and nothing super new conceptually, but just trying to cover more of the space, which is quite large of Python programs that are in this benchmark. We basically went from 27% to 42% overall on this programming puzzles benchmark. And int is well covered. String is pretty well covered. Float is well covered here. And there's a bit of a weakness with lists, and that's because I'm struggling a little bit to have a good encoding for lists that works for synthesis, and I'll come back to this. So really the main issue with not getting higher numbers is that kind of encoding things in an SMT solver kind of forces a functional reading that is not really compatible with synthesis. And some of the errors we include, so these would be, for example, soundness issues where we return SAT and we find a model, but it's actually failing on Python. So some difference in semantics between the Python level and the SMT level, and other cases where it's returning on SAT, which shouldn't be possible for this benchmark because we know there is a solution and things like this. So there is this kind of work to incrementally improve the results. But already we have some coverage. And one thing we tried is complementing whatever the solver can do with heuristics from LLMs. And so the thing that I showed at the beginning was an extrapolation where we give the smaller instance solution found using an SMT, and then the bigger instance is not solved by the SMT, but by the SMT solver, but we ask an LLM to extrapolate. And actually, this used to be quite good with earlier models, but with the 4.5 Claude models, it turns out that it's able to solve more puzzles without the hints than with the hints. So it's kind of tricky at the boundary of these tools to think, what can you give symbolically to an LLM so that it improves its performance? Or what can the LLM do heuristically so that it improves the solver's performance? And I think that's kind of still very open. And LLMs are already quite good at this. So for example, for the list strings puzzles, which are maybe more intuitive than than the int ones. Claude Sonnet 4.5 solves 79% of them. And so that's much better than what we got with the solver out of the box. And then one thing that didn't work very well is to do these constraint refinements. So starting with SMT-lib compiled code and thinking, how can LLMs augment it or use it to do something useful? But I haven't been able to get it to do anything useful with the compiled SMT-lib. And just, yeah, so this is just the result that without extrapolation, it does much better. And so I don't think I will have time for a demo, but I think I'll just skip to just some of the problems that we've achieved. So in terms of the issues, so I think there's really this verification versus synthesis gap when using an SMT solver in the backend to do not verification but synthesis. And really that's kind of like, if we had relational constraints, we would be able to express that that this is kind of the constraint that we want as a whole, instead of like shoehorning something into the functional side and then checking whether it's 1000 or not. So that is not very conducive to going backwards from here. And so I think in the next steps of this, I want to think about a relational SMT backend, thinking about maybe something like Minicarin for relational search, CHR for composable constraints and SMT dispatch, SMT for theory reasoning still, and because to avoid the bottleneck of always going back and forth between the SMT solver and the search, having some sort of multi-granularity dispatch, and also stage pre-computation. So what we've learned from this project is that, I mean, this basic idea of staging from Python to SMT is not completely new, especially in a more verification setting, but it's kind of easy to get started. It's easy to add more cases. It becomes very ad hoc somehow. You have to cover a lot of the Python semantics to get meaningful results. But conceptually, it's kind of the trick works. And then SMT hits a wall with synthesis. So functional encodings verify but don't invert. And this is where I think relational backends are needed. And LLMs are already strong at guesses. This benchmark that I'm actually maybe over specializing to in the setting wasn't in the context of like neural systems, and LLMs are quite good at it already. And it was a question to see how far I could push the symbolic side of this. And the scaffolding that we had to communicate between the LLM and the SMT quickly became obsolete in some sense between LLM and Holey. And so we can think of smaller witnesses helped older models, but not current ones. And soundness is easy in the system. It's just rechecking things at the Python level. And so it makes it easy not to trust the solver encodings or the LLM guesses. And so that's what I had for today. And I thank the people I discussed this project with and collaborated with. Thank you.
Do we have any questions? Yes.
Thank you for the interesting. Thank you for the interesting talk. I have a question about the LLM and the comparison of the performance of LLMs and Holey. So, like, are the results complementary, or the LLMs completely like subsumes the performance?
So I mean I didn't run the whole benchmark on LLMs. I should at some point probably, but I think it was in the case of the list string, for example, there were a few list string problems that Holey got and the LLM didn't got, but much more the other way around. So I think there can be some complementary things, especially with ints when you have arithmetic computation that is advanced. Yeah, so I find that LLMs, I also gave them a lot of leeway because they were allowed to make many guesses, and then I would just pick the ones that work. So it was pretty generous. But I would say I don't have critical data to say whether it's complementary or not. I know that there are some like significant non-overlap. Yeah.
Thank you.
Okay, let's thank the speaker again and move on to the next book.